Hello, we are Team 3. This is the analysis and redesign of a 3D printer. I am Cameron Miller. We also have Sarah Searing, Osvaldo Serrano, Joel Honigford, and John Radke. For a product description, we have a 3D printer. The 3D printer we analyze and redesign is an FDM printer, a fused deposition molding printer, which you can see here. It utilizes computer-aided design to create parts by extruding or feeding thermoplastic filaments through a heated nozzle, melting the plastic, and applying it layer by layer to an extruder plate. The production of this particular FDM 3D printer model is 66,000 units.
The primary customer is mechanical hobbyists who utilize the 3D printer for creating parts or models for their various projects where 52,800 units are used. The customer is concerned with a lower cost option while achieving quality products. The secondary customer is generally rapid prototyping teams within an innovation division of a company where 13,200 units are used. This customer is concerned with high precision and isn't worried about cost. We created a FAST diagram for our functional analysis. The task function of the FDM 3D printer is to create a product. To do so, the 3D printer must maneuver axes, which it does by maneuvering X, Y, and Z axis. It melts material by feeding material and adding heat. It layers material by applying material and dispersing heat. It assures dependability. It assures convenience. It enhances product with increased precision, and it pleases senses with reduced vibrations.
The following is our exploded view of our FDM 3D printer. The following shows all of our subassemblies and the exploded views of each. This function component mapping matrix shows the components within the 3D printer along the y-axis aligned to the functions of our FAST diagram shown previously along the x-axis. This matrix is crucial in ensuring our redesign does not interfere with the functionality of the components of the 3D printer as a whole. The quad chart classification details the manufacturing cost, low and high, and functional importance, low and high, for each part within the 3D printer. Based on the cost calculated in our bill of materials and functional component mapping matrix, there were no parts to be eliminated. Over half of our parts were to be kept as is, and we came up with the parts eligible for DfMA redesign as shown in the bottom right section. As we explore the product family design, we utilized the functional differentiation table to show the functions shared between the primary and secondary variants shown on the left, and the functions that differ, which include increased precision and reduced vibration shown on the right. By evaluating the function component mapping matrix and the functional differentiation table, we found that the modules would be the extruder housing front, extruder housing back, and the extruder mounting bracket.
We chose to modify the extruder mounting bracket and the extruder housing back seen on the left in order to modularize our design. The primary and secondary versions of our new design can be seen above as well as on the next slide. The following is our assembly sequences for both the primary and secondary versions. You can see that the primary and secondary version differ from the extruder housing assembly, which includes the extruder housing front and extruder housing back, to the linear guide mount. For design for manual assembly, we looked at the assembly sequence in the product family assembly diagram, performed the assembly analysis of the primary product variant, and calculated the total assembly time and assembly efficiency for our manual assembly. The number of parts calculated was 77. Our efficiency was found to be 0.04, and our total operating time was 437 seconds. After our redesign, our manual assembly time was cut down to 351 seconds. Our efficiency was increased by 0.01, and the number of parts decreased by 1. You can see below in the chart, before and after, the total times and number of items, manual handling codes, etc., for the flange shaft support and the extruder mounting bracket that we redesigned. Our flange shaft support had 5 different DFA principles applied: reduce fasteners, prefer snap fits, add features for easy insertion, provide locating features, and avoid adjustments. You can see on the right the new part and the snap fits, lack of additional fasteners. The snap features also prove to be locating features, We avoid adjustments by removing the bolt seen in the first part and added features for easy insertion. And then for the bottom part, the redesign here included 3 different redesigns for DFA principles, reducing part counts by including only 1 part instead of 2, reducing the fastener count as there are no fasteners to connect the 2 parts anymore, and provide locating features as seen on the front face of the bracket. After looking at our assembly sequence, we decided that we could redesign our parts for automated assembly. We started out with a required assembly rate of 12 parts per minute. We had 3 parts and a total cost of $7.58. After, we had 12 parts per minute still required with 1 part and a total cost of $5.60. You can see below in the table that we had a U-bracket, a stepper motor faceplate, and a linear guide mount. The stepper motor faceplate we do refer to as an L bracket as well. Those 3 components were then reduced down to 1, where you can see the linear guide mount on the lower portion. Those parts were chosen because of their location in our function component mapping matrix, as well as being in the redesign column on our quad chart. Here you can see how the U bracket, L bracket, and linear guide mount all became 1 part. So we utilized the design for automated assembly for reduced part counts, allowed hand and tool access on 2 different parts for the L and U bracket, added features to facilitate orientation on both the end of the L bracket and end of the U bracket to facilitate the orientation over top of the linear guide mount. We also provided locating features as seen on the linear guide mount to assemble to the linear guide, and then avoid adjustments. So we do not have the adjustments on the U bracket.
For the process selection of this part, we determined that the material would be a thermoplastic. It is relatively prismatic shape with low mass, relatively high thickness, and standard tolerances in a large batch size. The candidate process was determined to be machining as seen in this chart. The process selection for this part, similarly, the material was determined to be aluminum. It is a 3D solid of low mass and low thickness, or small thickness. Running through all of our candidate parts, we determined that die casting would be the optimal process for this part. For the design for manufacturing of this part, we first tried running it through DfM Pro. They gave relatively minor design changes, mostly to do with the edges of the part and the internal hole dimension. Using analytical methods, the before redesign was 1372, and the after of the analytical method hasn't been determined. Hubs we ran into some issues with. It did not seem to like our part. It would not run the analysis, so that's something we'll need to do in the future. The design for manufacturing went similar for this part, as we did find the process, as I mentioned earlier, but we were not able to perform the manufacturing analysis up to this point.
For design of product service system, we suggested a smart monitoring service system. It suggests maintenance intervals after a specific time of use, it tracks material usage, it suggests replacement intervals, provides information about replacing specific parts. It's easy support via website, live chat, email, frequently asked questions, or phone call, and it's a minimal cost to the customer. Some benefits the customers will experience is streamlined printer maintenance and material replacement processes, increased printer product lifespan, printer functionality and efficiency increases. The manuals are online, so you don't have to waste paper. You don't have to replace the printer as often because the lifespan is increased, and the maintainability and serviceability through easy customer support also increases the lifespan of the printer. For our design critique, we determined that our redesign had several benefits. First, it reduced the overall part count, reduced costs. Additionally, with consolidation of several parts, assembly would be simpler. Finally, the variance between the two designs roughly suited the needs of their respective customers without compromising the costs. In terms of cons, we found that with such a broad product with many moving parts, it became difficult to create cohesive designs that didn't alter another part. In the future, we would like to focus in on potentially one sub-assembly to perform DFMA on. Thank you very much.